Hey everyone, welcome to today's video. I'm Ben, and today we're going to be covering the properties of the integral. These properties are essential for your calculus classes because they allow us to evaluate integrals in a much more simple manner. Let's get right into it. So the three properties of integrals that I'm going to be covering today are the most important ones. Although there is a few more properties, I just don't think they're as important and they're not as common to see throughout calculus. And these three right here are really all you'll need. You'll be applying these really throughout every single integral that you do. And yeah, if you'd like to know more about the other properties, you can just search up online properties of integrals and you can see them. They're just not as essential and not as fundamental as these three. So let's get right into it. Looking at the first one, what we see is the sum and difference property. Really what this is saying is that if we have one integral composed of two functions, f of x and g of x, and they're separated by a plus and a minus, meaning that they're two separate terms, this allows us to separate them into two integrals, one of them being f of x, the other one being g of x. This allows us to just separate them, keeping the same bounds, and this is helpful for beginners especially, because if we have a complicated looking function but they're separated with pluses and minuses, we can just separate them into separate integrals and evaluate them one by one. It's much easier on the eye and can just relieve a lot of stress just saying, okay, I can just take one at a time. The next property is the constant multiple rule. This basically is saying that if you have a function being multiplied by a scalar, or a constant, c, we can go ahead and separate the constant completely from the integral. We can just pull it out, put it in the front, and just evaluate the integral, that means the function itself. And then at the very end, we multiply that constant back into the function. I'll be covering examples showcasing this, so don't worry. It's not as complicated as it sounds. It's actually very helpful. And yeah, let's move on to the next one. This is the reversal of the interval property. It's when we have an integral from b to a instead of a to b. Usually we have a to b, where a is the smaller value of the two. If we have a larger value in the bottom bound, where b is greater than a, we can go ahead and flip the bounds, making it a to b, but we must place a negative sign in front of the integral. That's it. Simple as that. I'll be showing some examples covering these, showcasing these properties, and making sure you understand these fully for your upcoming semesters. Let's get right into the example. So here we have our first example. We have the integral of x squared plus 2x minus 4. Right off the bat, we can see that we can apply one of our properties of integrals, right? We can apply the first one, the sum and difference. We have a plus and or a minus separating several functions, right? We can identify this as this is our f of x. Then we have like a plus, a g of x, some random function, just a function. G of x and f of x are just names that I'm calling these functions. And we have a minus. We'll call this last one h of x. Although there's no x in the 4, right? There's a negative separating it, meaning it's a separate term, meaning we can separate it into its own integral. So with these properties, let's go ahead and apply them. So let's go ahead and separate this in three integrals. Now we have the integral of x squared dx. Remember, always add your dx. Integral dx are one operator. And then we have a plus the next integral of 2x. And then we have a minus, remember, minus the integral of 4 dx. Boom. Simple enough. Now we can go ahead and approach each of these integrals separately to make it easier on us. Let's go ahead and work on the first one. Let's go ahead and work down here separately. We're going to go ahead and work on this integral right here, x squared dx. This is one of the most basic integrals that we can get. All we have to use is the reverse power rule. Recall that the reverse power rule is that when we have a function raised to some power, n being any number, it can be a fraction, it can be negative, it can be positive, it can be whatever. if we have this form, which we do, we have x to some power. To find the antiderivative of it, we're going to go ahead and add 1 to the power, n plus 1, and divide it by n plus 1. Simple enough. Let's go ahead and apply this to this case. So we're going to add 1 to the exponent, x squared plus 1 over n plus 1, 2 plus 1. Simplifying this, we get, which is 2 plus 1, just 3. So we get x cubed over 3. And that's it. That's the antiderivative for the first integral. Let's go ahead and just add that up here now to our final answer. Simple enough. Let's go ahead and work on the next one now. We have the integral of 2x. Now we can see that we can apply the second property, the constant multiple property. We have the form of a scalar, or a constant times a function, meaning we can go ahead and pull out that constant separately, pull it out of the integral and just focus on the function itself. So we're going to go ahead and pull out this 2 and just evaluate the integral, the function itself. Remember, if we don't see a power, we automatically assume it's just 1. So, reverse power rule, we bring that 2 along. We don't get rid of the 2, we bring it along. Focusing on the function though, we add 1 to the power, so 1 plus 1 over 1 plus 1. Simplifying this, we get 2 times x squared over 2. Or you can think of this as x squared divided by 2. So now that's it. But we can simplify this one more time with the 2's. Remember, we're multiplying these together. In multiplying, we can reverse the order. We can multiply them however we'd like. We can separate this into 2 over 2 times x squared. This is the same thing, just rewriting it for you guys' sake. Remember, 2 over 2, any number or anything over itself is just 1. So this is going to just turn into 1, meaning we're just left with x squared. Simple enough, right? Let's go ahead and add that up here now. X squared. Boom, almost done. Oops. Sorry about that. We're adding this up here. X squared. Next one, last but not least. Let's go ahead and evaluate this integral now. We have the minus 4 dx, right? Since we don't have an x there, you can think of this as 2 ways. When you see just a number, right, we can go ahead and pull that out. Again, although it's going to look weird, we can do it. We can go ahead and pull out that 4. We have a negative 4 now, times the integral. When we pull out the 4, this leaves us with a 1. Since it's not going to be 0, that doesn't make any sense. We're pulling out the 4 because if we were to multiply this 4 back in, we'd end up with this again, right? 4 times 1 is 4, meaning that we did this right. So now, if we just have 1, the antiderivative of 1 always is going to be x, just x, leaving us with negative 4 times x, or just negative 4x. This makes intuitive sense, right? What's the derivative of just x? It's 1. So that's why it's just x, right? So let's go ahead and add this to our final answer up here. We're going to put a minus 4x. And that's the final answer. One more step, almost forgot. Most important step is we always add a plus cheese plus c, right? When we're doing indefinite integrals with no bounds, right? We had no bounds in this case. We always add a plus c. We always add that plus c because there could have been a constant there in the original function, right? We're doing antiderivatives. That means that when we take the derivative of this function, we end up with our integral. We can even test that out. We can do the derivative of x cubed over 3, bring down the 3, subtract by 1 over 3, plus, bring this 2 down, right? Power rule, 2x minus derivative of 4x is just 4. Remember, plus c C is just a constant. Constants, when you take the derivative of just a constant, it's 0. So we're meaning that nothing's there. And now look, 3's can cancel out, and we go back to our original function that we integrated. And see how, notice how that plus C didn't change anything? Meaning that there could have been a constant in our original function, but it doesn't appear in the integral. That's why we always add a plus C. That constant could just be 0. We just add the plus C just in case there was a integral, a constant in our original function. So boom, that's it for the first example. Let's move on to the next one. Next example, we have the integral of 5x to the 4th power plus the square root of x minus 1 over x. Let's go ahead and attack this integral. Let's go ahead and separate it into 3 separate integrals using our sum and difference property. So we have the first integral of just 5x to the 4th dx plus the integral of square root of x minus the integral of 1 over x. Sorry, we always have a dx here. Even I forget that. So let's go ahead and approach these one by one. 5x to the 4th, right? That shouldn't be too bad. We know how to do that. So we have the integral of 5x to the 4th dx. Remember, constant multiple rule, bring out the 5. Now we have a pretty clean function to integrate. Just x to the 4th. Reverse power rule again, right? We have x to some power n. So we're going to bring the 5 along, multiply it. We have x, 4 plus 1 is 5, divided by that new power, 5. Remember, these 5s right here turn into a 1, right? So now we just have x to the 5th power. Simple enough. That's our first one. Next one, we have square root of x. For a lot of beginner students, square roots are very intimidating. They can be more complicated as further down the line, but when we just have the function just x squared, or square root of x, it's very easy to approach with the right techniques. So let's go ahead and do this. We have the integral of square root of x. Recall that the square root is just another way to write a 1/2 power. That's just another way to write the 1/2 power. So let's go ahead and rewrite our integral in terms of the power of 1/2 power. So we have x to the 1/2. And look, we have another case of a reverse power rule. Although we have a fraction, we can still apply the reverse power rule. N is just another number. So let's go ahead and apply it. So we have x to the 1/2 plus 1, right? Divided by 1/2 plus 1. 1/2 plus 1 is 3/2. We can see that 1/2 plus 1. We get a common denominator for the 1. We get 3/2, right? This is basic algebra right here. So now we have x to the 3/2 over 3/2. It's always going to be the same as the power. And this is not very nice to look at, right? X to the 3/2 divided by another fraction. We don't like that, right? We can actually go ahead and simplify this to not make it look like a weird fraction. Recall that dividing is the same thing as multiplying by its reciprocal. Reciprocal meaning multiplying it, reciprocal meaning flipping the fraction. So flipping 3/2, we get 2/3. We have to multiply it though, times x to the 3/2, like such. Remember, yeah, that's always important to do. You'll be seeing this a lot in your calculus classes. I recommend taking notes on this right now, making sure this is in your notes so you can always go back to it if you're ever confused on what to do. So yeah, simple enough. This is the final answer for this integral. We can go ahead and leave it like this. Now let's go ahead and attack the last one. We have the integral of -1 over x dx, right? Dx. So remember, I brought that negative out because we can think of the negative as being multiplication by -1. Remember, with constants, negative 1's a constant. We can pull it out to the front, meaning we have this negative 1 at the front. If that helps you guys see easier. So now, 1 over x. This is a unique case where we cannot do the reverse power rule. Reason why is because 1 over x, we can rewrite that as x to the negative 1. Remember, that's basically exponent rules. You have a power in the denominator, you can flip it up, make it a negative power. Here, we couldn't do the reverse power rule. What if we added 1 and did this, right? We'd get 0. We'd get x to the 0 over 0. Doesn't make any sense. We can't divide by 0. So, So whenever we have the case of just 1 over x or any number over x, right? We can always pull that number out to the front, giving us this 1 over x. This is called a table integral. This is just a common integral that you must know. You can either have it on the sheet of notes or memorize it. Whenever you have the function 1 over x, it's always going to be equal to natural log of x, absolute value of x. So we have this negative natural log of x. That's just a very unique case. Whenever you have a 1 over x, it's always going to be ln of x, natural log of absolute value of x. So let's go ahead and put all these together for our final answer. So going back up here, we had x to the 5th plus 2/3 x to the 3/2 minus the natural log absolute value of x plus c. Remember, always add the plus c because we always need to account for that possible constant that could have been there. Boom, easy enough. Just with enough practice, enough repetition, these should be cakewalk for your upcoming classes. Let's go move on to the next one. Our next example here is going to be, we're going to be doing a definite integral with bounds now, and I'll be showing you guys how to evaluate definite integrals if you have forgotten. So we're going to have the integral from 3 to 0 of 3x squared plus 5x dx. Not too bad, right? Not too bad. But we notice, right, that our lower bound is greater than our upper bound. In this case, referring to our properties of integrals, when our lower bound is greater than our upper bound, we flip it and we add the negative sign to the front. Let's go ahead and apply that here. So we're going to go ahead and flip the bounds, put the 0 down here, and put the 3 up here, and make it a negative sign. And then we keep the function in the inside the same. Simple enough. Now, let's go ahead and approach it. I think if you guys are comfortable with the properties now, we can just realize that, let's just scratch that. Let's go ahead and let's just keep applying the properties so you guys can get used to that. So let's go ahead and separate this into two integrals. Let's go ahead and evaluate the first one. So we have 3x squared dx, right? Reverse power rule, remember? So we have this 3 times the x squared plus 1 divided by 2 plus 1. Simple enough. So now we have 3 times x cubed over 3. Remember, 3's cancel out. They just turn to a 1. We get x cubed. Simple enough, right? Next one. We have 5x dx. So, remember, reverse power rule again. You'll be seeing this. Reverse power rule is the most important rule that you need to know. Soon, after just doing it enough times, it becomes just muscle memory to know that when you see an x or x to any power, add to the power, divide by the new power, right? So now we have 5 times x to the second power, right? It had a 1 originally. 1 plus 1 is 2. Divide by the new power. 5 over is 2. So this is it. We can leave it like that, or we can just, I always like to just combine the number being multiplied by the fraction. So we have 5 over 2 times x squared. These are equivalent statements right here. These are the same things. Don't worry. Don't be scared. So let's go ahead and just apply this now. Remember? Let's go ahead and put this in the front now. Let's go add it to our final answer. So we have x cubed plus 5 over 2 x squared. But we need to make sure we account for that negative in the front. Sorry, I should have made that more clear. We have that negative to the front, and we need to evaluate our integral now with our bounds. Meaning, if you don't remember, so the capital F represents antiderivative. We're gonna go ahead and plug in our top bound minus the antiderivative evaluated at our bottom bound. Let's go ahead and do this now. Apply this. So this whole thing right here is our F. So let's go ahead, and this is usually the notation for evaluating is like a bracket or a straight line with our bound 0 to 3. So let's go ahead and just put the negative sign in front, right? So now we have our x cubed. We need to plug in our b value into our antiderivative, which our b value is 3. So let's go ahead and plug that in. So we have 3 cubed, right, for the x cubed, plus 5 over 2, 3 squared. Simple. And then we need to do a minus, but then remember, it's minus because we're subtracting the entire antiderivative. Our antiderivative is negative. The whole thing is negative with that negative in the front. So it's going to be negative. We're going to have another negative, parenthesis. This looks a little weird, but stay with me. Now we're going to go ahead and plug in the bottom bound. But in this case, which is nice, it's our bottom bound is 0. When we plug in 0 into our antiderivative, everything should turn into 0. So let's go ahead and look at this. So we have 0 cubed plus 5 over 2, 0 squared. Remember, 0 cubed is just 0. 0 squared is 0. 5 halves times 0, 0. So this whole side right here turns to 0. So let's go ahead and bring this down. We have this negative, and we have 3 cubed, which is 9. Let's go ahead and pull up the calculator. We have, what should this be? 27, right? 3 times 3, 9 times 3, 27. Plus 5 halves and times 3 squared, which is 9 times 9. Simplifying this a bit further, we have 5. Remember, this is a fraction multiplication. Pretty simple. Just multiply the top and multiply the bottom. 5 times 9 is 45. So we have this 45 over 2 times 1. Just 2. And this is a perfectly valid answer. Most professors would accept this. But in this case, let's go ahead and simplify these fractions just to show you guys a bit more. So we have 27 and 45 over 2. We need a common denominator. This 27 is over 1. To get a common denominator, we need to multiply the top by 2, multiply the bottom by 2, getting us 54 over 2, and we have a negative, plus 45 over 2. And 45 plus 54, I can probably figure that out in my head, but let's just make sure we don't mess up. 54 plus 45 is 99. So now we have this negative in the front. We have a 99 over 2. Simple. Boom. We can go ahead and just drop the parentheses since it's just one number. So now we have a negative. Our answer is negative 99 over 2. That's it for that answer. That's it for that problem. Not too bad. In this case, we did a definite integral, with their bounds. But always remember this formula. It's our antiderivative evaluated at the top bound minus the antiderivative evaluated at the bottom bound. Let's get right into the next example. On to the last example. Let's go ahead and do a spicy example. One that is going to look a little tricky, but we're going to use a whole bunch of tricks in order to solve this that I think are important for you guys to know. So you guys expect anything that your classes throw at you. Let's get right into it. So the integral that we're going to be evaluating is the integral from 1 to 2 of, we're going to be using v as our variable, or let's go ahead and use t. We have t cubed plus 3t to the 6th power over t to the 4th dt. You're like, what the heck? How do I solve this? We can go ahead and simplify this to the furthest extent, make this look super easy so we can evaluate it right away. Let's get right into it. So first thing that I notice here is that we have two terms in the numerator being divided by the same denominator, right? With fractions, if we have the same denominator, right? So for example, if we have 2 over 2 plus 1 over 2, how do we add that, right? We just add the top. We do 1 plus 2 over 2, right? Obviously 2 plus 1 is 3, but in this case, I'm leaving it like that so you guys can see that we can, so if we have 1 plus 2 up here, you notice that we can go backwards. We can split it again, right? We can go back and forth. We can have 2 over 2 plus 1 over 2, or we could have 1 plus 2 over 2, right? So with this logic, why don't we go ahead and split this integral into two separate fractions as such? So we have the t cubed over t to the 4th plus 3t to the 6th over t to the 4th dt, right? Does this make sense? I hope this makes sense for you guys. Well, it's the same thing. It's the same thing. You know, we have same denominator. We could, if we wanted to, combine this to make it look like this again. But in this case, this is actually going to help us out. So remember, we have a plus and we have a minus, or a minus, we have a plus, meaning we can separate this into two separate integrals, right? Let's go ahead and do that. So for this first one, we have t cubed over t to the 4th dt, right? Remember, we have this, when we're dividing fractions, we have the same base, meaning that we subtract the exponents from each other. So t cubed over t to the 4th is the same thing as t cubed minus 4, leaving us with t to the negative 1, which is going to be, t to the negative 1 is the same thing as 1 over t. Remember, negative exponents means it's in the denominator. So we have 1 over t dt, right? Pretty easy. It looks scary at first, but now we have 1 over t, which is the same thing as 1 over x, or 1 over any variable. Remember from the last example, we had a 1 over x, and the antiderivative of that is just natural log of x. So here, this is going to be natural log, absolute value of t. Boom, simple. We'll go ahead and evaluate them afterwards when we combine all of our antiderivatives together. So let's go ahead and move into the next one. So now we have 3 t to the 6th over t to the 4th. Remember, that 3 is just a constant multiple. You can go ahead and bring it out, like always. But you have to remember that it's being multiplied. You can only separate them when it's being multiplied. You can only bring it out of the integral, when it's multiplied. If it was 3 plus t to the 6th, you could not bring it out to the front. So now we have t to the 6th power over t to the 4th dt. Remember, like the last example, on the last step, if you have a same base and they're being divided, you subtract the exponents. 6 minus 4, which is t to the 2nd. So now we have the integral, 3 times the integral of t to the 2nd power dt. Remember, reverse power rule. So we're going to bring along the 3. We're going to do t. 2 plus 1 is 3 over 3. The 3's cancel. Remember, 3 over 3 is just 1. So we just have t cubed. So now let's go ahead and combine all these together. Going back to our main original problem, we have natural log of t plus, what did we have? T cubed. But then now we need to evaluate it, our antiderivative, like such. You'll see either a bracket or it's a straight line, meaning we're going to go ahead and evaluate it. So let's go ahead and evaluate our antiderivative, which is, the notation is capital F, with our top bound first. So let's go ahead and put parentheses so we can separate everything, make it look organized and clear so we don't get confused. So we're going to go ahead and do natural log. We can drop the absolute values now since the bounds are positive. We don't need to worry about the absolute values. So we have natural log of 2 plus 2 cubed. And then we can put a parenthesis and then minus the separator. Remember, it's f of b minus f of a. Remember that? Let's go to minus, and then the whole antiderivative again. Natural log of 1 plus 1 cubed. That's it. So we can go ahead and simplify some things. 2 cubed is 8. So we can't really simplify natural log of 2. It's just a long decimal. So we're going to go ahead and just leave natural log of 2 plus 2 cubed is 8 minus natural log of 1 is actually 0. If you guys don't know too much about your natural logs, I might make a video on that. But remember, natural log of 1 is 0, natural log of 0 is undefined, and natural log of e is 1. Those are the main ones you need to know. So I can maybe make a video on that in the future because it's really important. A lot of students don't really remember their log properties either. So this is just going to be 0. So this is going to be minus 0 plus 1 cubed is 1. So with the FOIL in this negative, like always, you have natural log of 2 plus 8 minus 1, which is natural log of 2 plus 7. And that's the final answer. Sorry, let me make that look a little nicer. Boom. That's the final answer. Remember, no plus c's because this is a definite integral. We have bounds. There's no need to do plus c. With these integrals, we're calculating the area underneath the curve. The curve in this case was t cubed over t to the 4th, whatever. But yeah, that's it for this video. I hope you guys really enjoyed and you took a lot from this. You learned a lot from this. I will be posting a lot more videos in the upcoming weeks. The next video I'm going to be posting, I think, is going to be on U substitution, which is one of my favorite techniques. It's the most essential. It's used everywhere, and it's very powerful. Although it's a very basic technique, it's actually very powerful. So I hope you guys stay tuned. Make sure you subscribe. Leave a comment down below. Any suggestions, any feedback, whatever. I'll be reading all of them. Follow me on my social media pages. They might not be created at the time of this video, but they will be created soon. So yeah, thank you guys for watching. Hope you have a great rest of your day.